And Susan, I'm going to pass over control to you.
Hello everyone, and welcome to the CHP Partnership webinar on CHP as a boiler replacement opportunity. It's my pleasure to welcome you today, and we have a number of really expert speakers that will share their experiences with you, and hopefully you'll have a lot of questions for them, and so we'll use that time at the end to cover that. So let me just do a brief round of introductions. So our first speaker will be Jay Wiest, who's a professional engineer with business development director at Worley-Parsons, and he will bring from the sort of project development perspective. And then we have some facility operators that will be joining us from Penn State University, Paul Moser, Superintendent of Steam Services, and Laura Miller, who's Senior Energy Engineer. And so they'll be sharing their experiences actually with two systems, one that's been put in and one that's in the works. And then, like I said, we'll have a question and answer session moderated by Bob Seidner. So first, a couple words of introduction. I think a lot of you are probably already familiar with the EPA-CHP partnership, but perhaps you're not as familiar with what we're doing lately. So we are a voluntary program that focuses on promoting CHP as a highly efficient way to reduce the environmental impact of power generation. And so we have a lot of tools and resources to assist with project development, and we also target barriers, regulatory barriers, financial barriers, that sort of thing. Through the over 12 years of the program, we have 770 projects that we've helped. We have over 450 partners and quite a few megawatts of capacity that we have facilitated. And I would also just make a note that, so we have today's webinar, and we plan another webinar in June that's going to focus on commercial PACE and CHP. So please do stay tuned for further announcements for that. And real quickly, let me just set the scene for you. So we targeted this topic as something that we thought would be based on feedback we got from partners and speaking with others that could benefit from a closer look. So we developed a fact sheet that we published about a month or so ago, and it's on our website, and you'll see the URL here on the slide. So what we're trying to do is really illustrate the potential economic, operational, environmental benefits of CHP systems in terms of looking at old boilers. This is just a little statistic about how many boilers there are that are 40 years old. It's quite a few in this country, and facility owners are looking at increased maintenance costs. There are new regulations that are coming into being, and perhaps they have new steam demands that have developed since they have the systems went into operation some years before. So there's a number of reasons why folks might be looking at a boiler replacement option. And so we thought it would be useful to present a comparison between CHP and natural gas boilers. So that might be a logical option for people to consider, but perhaps if you dig into the numbers and the details and your needs on site, you may see that CHP would also be something you'd want to consider. So we look at a number of different factors in the analysis, and for a number of facilities, we think that CHP would be a financially attractive option. So I would commend that reading to you if you haven't looked at it already, and we definitely appreciate feedback on that. So please do share any thoughts you have about when you get a chance to review that fact sheet. So without further ado, let me turn to our speakers who I introduced already, who will be providing you with some real-world examples of how boiler replacement happens, elements to consider, and kind of the challenges and lessons that they've learned in doing this. So thank you very much.
Okay, thank you, Susan. This is Jay Wiest at Worley-Parsons. And as we go through the slides today, what I have laid out here as requested is an approach to evaluating CHP as a boiler replacement option, and maybe most likely from a project developer perspective and looking at the options. And then from there, we'll close out, and I have a case study or two that we could get through and show you a real-life example of what the opportunity is and how to evaluate this. If you could go to the next slide, Sarah. First of all, Worley Parsons, we are a project delivery organization for execution of projects, helping our clients, develop projects and then deliver them from concept through completion. And as you can see, we are a global company of about 40,000 people located around the world and operating primarily in the power, hydrocarbons, mining, metals, infrastructure, environment, and minerals and chemical sectors. Next slide, please. A key consideration as you approach the CHP project and looking at any type of project delivery is to look at the concept all the way through to completion. And really, as far as what we see at Worley Parsons as a project delivery approach, is taking that blank sheet of paper, looking at what your options are, and then from a feasibility select consulting perspective, take the next step, transition through a staged, gated process where you develop the project in both scope, concept, and details, along with the budget needs as far as determining capital and O&M operating budgets and developing pro formas for a bankable feasibility study and then actually building the facility and then operating and maintaining it, is that project moves along a development cycle, as we call it here, project delivery and project development cycle, going from a consulting phase to a detailed engineering phase and through an own and operate phase and maintaining the facility. And that's really the approach we take as we step through the process here for looking at, okay, if I wanted to consider what CHP options I had for my facility and what are my alternatives when I'm looking at what was presented here from Susan as far as consideration of options when you're saying, okay, I have an existing facility, might be affected by boiler MAC, and that what are my options going forward. So as we go through this, keep that in mind as you would go through this process. And if you go to the next slide, please, Susan, Sarah. Why CHP, which is the question that you propose to yourself, and go to the next slide. And really what the value is here, you know, and I know we're talking about boiler and gas-fired boiler options, but if you're looking at boiler MAC, certainly the value proposition that you see is, you know, you're looking at, okay, do I want to continue at this point investing in my coal-fired plant operations and looking at retrofit air quality control to meet the boiler MAC requirements, and the things associated with that is maybe higher O&M costs, that would be over existing operations, increased maintenance for existing equipment. You know, there's really no return on invested capital, risk of escalating coal costs, and you're still exposed to future regulations which might be incurred for continuing coal burning. An alternative to that is to look at, okay, what is my gas-fired CHP option? Is, for one, you're going to have lower O&M costs, leverage CHP for producing electricity and supplementing plant load or cell excess power. You have a natural gas, you have a current market where natural gas pricing, you know, at least in the near-term horizon, sees somewhat stable. And then you have a possible higher return on investment and lower O&M costs through external electricity sales and improved plant profitability. Go to the next slide. And as you get into this, and these are developing issues that are occurring and just gaining traction in the industry, is other things to consider, and we're well covered in the CHP as Boiler Replacement Opportunity fact sheet that was just issued by the EPA. And these are things that you have to consider additional value and things that, as far as risk mitigation techniques and planning for future operation, where you look at your ongoing existing operations, and it might align with current corporate sustainability compliance implementation plans, that you're aligned with that by looking at CHP versus existing coal, or even as we go through the presentation, gas-fired package boilers. Is there site expansion needs for increasing steam demands? You have economic and operational benefits in consideration of this, where certainly a gaining issue that is gaining traction is enabling system resiliency and energy infrastructure, and this is really considering island mode operations. It's gained a lot of notoriety with some of the recent weather events in the Northeast, either snow or hurricanes, where there's been extended outages from the regions, and maintaining continued operations and avoiding, you know, for industrials, avoiding shutdown startup costs for unplanned outages. And as you get into those facilities which are institutional types with hospitals or nursing care or universities where there might be more critical benefits as a critical infrastructure, there are those too that provide island mode operation during those long-term extended outages. Other operational benefits and economic are hedging against rising electricity costs, and we'll get into a little bit of why that is occurring. Avoiding costs of new regulations, again, where you might have increased regulations in the environment for coal and oil-fired boilers, and then the environmental benefits, which is reduced greenhouse gas emissions and other criteria air pollutants, hazardous air toxics, solid waste associated with firing coal and oil where you have air quality equipment and normal waste streams, and then even as recently as wastewater issues that might be coming up as associated with coal burning. And then the other environmental benefits is just the increased efficiency, converting energy into thermal and power and doing it very efficient through a CHP process. Next slide. And this is just a summary of where we're at, certainly looking at the separate heat and power historical way of doing it with a thermal supply and then buying electricity which is generated and looking at the overall combined efficiency of that and comparing that to CHP. And I'm not going to dwell on this, but certainly this is the backdrop for what we're considering. Next slide. So let's just go through, okay, if really CHP is to be considered, what are some site design conditions and analysis on how you approach this? Next slide. And really, I mean, you set up the objective is you want to see what the benefits are. So you really look at your facility as either industrial, large institutional, or even commercial. And the way we've approached this is to say, okay, if you're going to do a quick screening analysis approach, as far as if I want to understand what are all my options and be able to quickly assess and screen them down from a multiple field of options, if it's 4, 5, 10, 15, 20, and get it down to 2 or 3 which are viable, this is an approach that you can actually take. And this is our approach, is where you set up some ranges of power generation capabilities, a range of steam generation capabilities within a modeling-based approach, and then look at the steam conditions that are primarily out there, and this is what we found, is either 150-pound saturated or 600-pound, 750-degree steam conditions are those that are good points of reference to be used as a starting point, and then from there you can get more site-specific. And then looking at redundancy, as far as looking at steam backup and with aux boilers in the approach, and then for power is assuming maybe that the power supply could be backed up from the grid. Looking at fuel supply, as natural gas being available for gas turbines and the heat recovery steam generator, and then for the aux boiler for reliable supply, just in case that there would be a loss of gas, is you could have an aux boiler dual fuel fired, which is oil and gas. Then the prime movers selection, and then using grid backup. Next slide. Is also some other considerations is power purchase situation, is developing a scenario where you might be selling excess power or just supplying the plant needs. Always emission compliance is important and meeting the environmental emission requirements, and that's on turn down, especially with combustion turbines, and making sure that your facility can always be compliant with your permit limits. The flexibility of operation, certainly we understand that with industrials, thermal requirements are what's the purpose of the facility, with power being secondary. So having that operational flexibility where you're always meeting thermal requirements and going from there for the added benefit. And CHP scope, certainly in understanding what the scope of the project is and the boundary limits, and then developing cost of capital costs and operating costs around those, operating and maintenance costs, are important for the evaluation. Then an economic inputs, and just looking at the data for how you want to do the analysis. Next slide. And this is just not that we're here selling equipment, but as a predetermined modeling is our approach was that we've set up predetermined heat material balances to consider the realm and breadth of the capabilities of each of these systems, and built modeling around that as a basis of doing a quick screening. And those are the increments that we list there. And then really the configuration is based on your site requirements. If you're considering CHP is looking at either, if you have a high thermal to power ratio, you want to look at simple CHP with a gas turbine and HRSG. You have a combined cycle CHP with a back pressure steam turbine. And then if you really are high in power consumption versus your thermal, you always have the combined cycle with the condensing extraction steam turbine option. Next slide. So the approach is look at your current operations and see, and going forward, what are the costs associated with that. Another option always is, and is considered today, is looking at fuel switching, which is gas burners on a coal boiler. And third option is just putting in gas-fired package boilers. And then finally, what we consider an envelope of CHP options is using a gas turbine or a reciprocating engine-based system and looking at alternatives and what that would be. Coming up with a capital, operating, and then doing a net present value, simple payback, and IRR. Next slide. And the things that you need to consider in the screening model as far as site data is and inputs in your evaluation is min and max steam requirements to make sure you can meet the site operations in the extremes, gas turbine attributes of efficiencies and fuel consumption and external exhaust temperatures, minimum fuel gas pressure requirements, project schedule, utility consumptions, import-export if there's options for that, certainly CO2 reduction for CHP versus non-CHP with coal, and then looking at the displaced electricity, if you would to include it or not to include it. Certainly our approach is fuel chargeable to power, which is a traditional CHP evaluation approach on how you value what incremental fuel is needed for heat rate and also for calculation of generating your own electricity. And then finally, thermal to power demand ratio and the electricity price gas ratios. Next slide. And then running it through an economic model. And, developing, you have a CapEx, you have a construction schedule, and you run it through an economic cash flow model and continue from there in developing the NPV. Next slide. And these are some of the benefits that we've found in general. Every site's going to be unique, but we have generally seen 40 to 60% energy savings. With an FCP heat rate basis, we've looked at systems at heat rates of 3,800 BTUs per kilowatt hours because of the design requirements. The one thing to be straight on is that, when you look at the capital budget for a CHP versus package boilers or retrofit air quality, it will be higher, order of magnitude higher in the estimate. And then, but the offsetting challenge or the offsetting benefit is the lower operating and maintenance costs and fuel costs, and looking at and evaluating that against the higher capital. And let's go on to the next slide. And I just want to run through a quick case study which shows these results. And if we go on to the next slide, this is for an 8 megawatt CHP, which is at a facility, and you can see the requirements here as far as their current power price, the amount of electricity they consume, what their steam demands were, and I emphasize were, at 144,000 pounds an hour with their coal-fired plant, and then looking at their coal pricing and natural gas pricing that's available at $379, $450. Next slide. And really the options here were a new package boiler with back pressure steam turbine. We evaluated Centaur 50, 70, and 100 as far as the benefits, and looking at those of producing both the power requirements for the site and thermal requirements. Next slide. And here you can see in both the Centaur 50 and 70, if you look at that, in those scenarios, they weren't quite enough to meet the thermal requirements, so you'd have to run an aux boiler in the background. And then with the Mars 100, they're producing more power than they need, so they'd be exporting power. And then looking at an extreme case is they have the Titan 250, and going from there. Next slide. And these are just, and this is really the true benefit, is looking at the levelized cost of energy, is that you can see the annual energy cost, what the savings are for spending the increased level of capital. Going from the $25 million for just the fuel switching, which is the annual energy costs, to the highest end, which includes the net benefit from selling power to the grid of between $5 and $8.5 million. Next slide. And then here, this is the total project cost, is considering, well, what do I have to pay to install these systems? And you can see to the left the simple solutions of retrofitting the coal or boiler fuel switching, or just putting in package boilers against some of the incremental costs of looking at incremental CHP options of putting in the combustion turbines. And next slide. And then just looking at the present value of the total energy. This gets into the analysis. This doesn't include capital, but just shows you over the life cycle analysis what some of the present value and what the order of magnitude differentials are that you can consider in your valuation. Next slide. And this is the breakdown of the annualized costs as you consider debt coverage, energy bill, and all the other operation of the facility. Next slide. And this here shows you the incremental CO2 reduction and the benefits that you have from that as far as you increase your power output and thermal requirements and efficiency of conversion is that you're actually saving CO2 not from your own facility but also what you're displacing from that you're generating yourself efficiently versus what's being generated from the local grid connection. Next slide. And this is what you would see in an NPV analysis, looking at to the left side the breakdown of what contributes to the net NPV, and if you see the above the bar on the left side is that's indicating the revenue benefit from selling the excess electricity to the local grid, and then giving you a net NPV that go to the right side of each of those bars, which might be less than the additional costs. Next slide. If you do a screening analysis, then you can see which might be the lower NPVs, but if you go into IRR and simple payback, is you can see for this, and this is in reference not to a base case, but in reference to a package boiler, which would you be buying new, that even with CHP, compared to a package boiler, you're still seeing a net payback period in the area of 4 to 5 years, and IRRs in the 20 to 30% range for the various options to show that there are some benefits yet economically, even as you compare to the savings in compared to a new gas package boiler. Next slide. And just some sensitivities for these options as you look at, okay, what's the variability of gas pricing? How does that affect my payback? And if you go to the next slide, is the sensitivity to the local electricity purchase price and how that affects the payback of the project. And if you go to the next slide. Another thing that you can calculate as you approach CHP is what's the cost of steam produced, is just allocating the capital, the O&M budget. You can see your steam required as far as the cost per 1,000 pounds. And if you go to the next slide, here you can see what the cost of electricity produced would be. You can calculate what it would cost in each of the options, and this is the annual average, so it does blend in if you have to purchase a portion of it. But you can see to generate yourself what the benefits are versus purchasing it from the grid. And if you go to the next slide, and then if we fix the steam costs at the current cost of steam production, you can see what the normalized cost of electricity production would be compared to fixing the steam cost versus calculating it. And if you go to the next slide. So that's the case study. As far as part of the presentation, I do have a second case study available, but as the time is available today is we'll be moving on to the next presenter, which is Paul Moser and Laura Miller at Penn State.
Okay. Good afternoon, everybody. Let's get started. Thank you for inviting us to present. It's good to see some friends in the crowd. And we'll get started with our story of what Penn State is and what our system looks like. Walk you through the East Campus Steam Plant project that is complete now. And we'll bring you up to date to where we are today. So Penn State University, right in the middle of Pennsylvania, about 50,000 students, faculty, and staff any given day here. And myself representing STEAM Services and Laura representing our engineering. So the way I'll do this is I'll take up to East Campus Steam Plant, then I'm going to hand it over to Laura and let her walk you through our next steps. Personnel-wise here at Penn State, we have 10-plus engineering and technical support folks who are helping us develop these projects. And here at STEAM Services, we have more than 40 people that are operating and maintaining the plants. We serve more than 200 buildings on campus with the steam system from 2 different power plants. A little picture of our district energy system here, Penn State. If you look down in the lower left, you'll see the WCSP, or the West Campus Steam Plant, and over here to the right, you'll see the East Campus Steam Plant. Together they serve the shaded areas that you can see. Those are the buildings we serve the steam. This had plus 200 buildings. The yellow hub of the wheel, if you will, is our walking tunnel. We're supplying that tunnel with high and low pressure steam, high being 150 psi and low being 13 psi, produced only from the West Campus Steam Plant back pressure turbines. So we've been combined heat and power here at Penn State since West Campus was built in 1929. Peak steam loads in the wintertime are around 420-some thousand pounds per hour, and our minimum steam loads in the summer about 80,000 pounds an hour. So we have a fairly dramatic profile there. It's about 5 to 1. That really owes itself to the cost of electricity here. When we developed this project back in '06, our price of electricity was about 3.5 cents per kilowatt hour all in. The prices of fuels at the time of the 2006 project were were gas around $13 per million BTU, coal being $80, $90 a ton, somewhere around $4 a million BTU. West Campus Steam Plant, the coal-fired power plant here at Penn State. Okay. So we don't use steam for chilling really at all on campus, so we really don't have a chilling load in the summer. Just a picture of where the West Campus Steam Plant, right in the middle of State College. It's the corner of Burroughs Avenue and College Avenue. And again, that's a coal-fired power plant. Annual tonnage of coal at the time was 75,000 tons of coal. Any winter day, we would have seen 25, 30 trucks a day of coal right here to the West Campus Steam Plant. You're looking at a natural or a bag house connected to the chimney there. And East Campus Steam Plant, located a little bit further out, and you can see it here. It's 2 packaged boilers there, 100,000 pounds an hour each. They're natural gas fired with fuel oil number 2 as a backup. Okay, so the energy picture in 2006, we needed additional capacity. We had our peak steam demand in the wintertime was approaching our N-1 capacity. So we were seeing increasing steam demands each year. So that was a big one. We had an aging infrastructure. So East Campus Steam Plant, built in 1971, was the last major upgrade to the steam system, or 40 years ago, last major upgrade to the steam system with campus growth. Yeah, with campus growth. So, so we went 40 years without a major upgrade to our steam generation system. Essential services also. This was shortly after the Katrina event and others, and a lot of us in our field started asking ourselves the question if we were prepared, and found that our answer really was no. And so this was how we defined it. Essential services: how and where would we care for about 10,000 people on campus should we have a total loss of power, something we really had not experienced, but we had seen others of our friends in the Northeast experience total loss of power. And we felt we needed about 12 megawatts on site to meet the essential services. So we were looking for a way to solve those problems. And so why did we pick CHP? We felt that it solved the energy picture that I just described. We also felt that it was a better commitment to energy efficiency. Instead of the boilers and the emergency generator sets, specifically on the EG sets, having a a CT that was running all the time would prove that it would be available when we needed it. And so we've been going with that philosophy. A little picture of the East Campus steam plant. And what you see here are a couple, 2 times 172,000 pounds or gallons of diesel fuel out front, so our backup fuel. And the addition here is what's housing the CT and the HRSG. So what we did here was add additional boiler capacity. We did not replace boiler capacity. We needed additional. Over here you see the original building that held the 2 times 100,000 pound an hour package boilers. If you went inside, you'd see this in the addition. That's our Solar Taurus 70 combustion turbine. And if you were to take the box away, you'd see the engine that looks like this. This is the way it looked in San Diego before they shipped it to Penn State. And it's connected to a Rentec boiler rated at 117,000 pounds an hour. Saturated conditions, 220 psi, delivering the campus somewhere around 140 or 50, whatever the campus high pressure steam demands are. So just a little view of what the cycle looks like. So bottom here is our combustion turbine with the natural gas or oil added. We're going to run this on gas under all conditions. Oil is really just strictly a backup, and it's nominally rated at 7 megawatts. It'll make a little over 8 megawatts on a cold winter day, and it'll make just under 6 megawatts on a hot summer day. Its exhaust temperature at 900 degrees is feeding a boiler, and it's producing steam without any duct firing at 32,000 pounds per hour. And we can add duct firing to this, which we are doing almost all the time, and we can bring that up to a total of 117,000 pounds per hour. And on a cold winter day here at the East Campus plant, this unit's usually running at 100,000+ pounds an hour. That's where we're trying to keep it at a minimum. We'll run it above that. Okay. So just some project costs. The CT was close to $4 million. The HRSG was $1.5 million. And in order to fit this into the existing plant, we had to build up the balance of plant. So the plant was designed for the units that were there, not the units that aren't there. So we added feed water capacity, deaeration, a pump. We added water treatment in the way of softeners and reverse osmosis demineralizers, and really a full build out to accept this machine. We're using the Solar service agreement, and that means they're going to be in here twice a year, once in the spring, once in the fall. In fact, next week they'll be in here to do a out-of-service inspection, and in the winter and the summer we'll do an in-service inspection, and then we'll expect a complete overhaul after about 30,000 hours. And these costs that you see below are the costs that you're basically investing so that you're prepared to go for the complete overhaul. And we have not had one yet, but when we do, we just expect that the engine will be removed and replaced with another engine, and we'll get going from there. So our projected electrical generation, a little bit on the electricity. Prior to putting in the CT, we are producing electricity here at the West Campus steam plant using steam turbines and producing back pressure steam to campus. So our electrical load always followed the steam load. In the summer time, we would make really just about 500 kilowatts of power. In the winter time, we could make a little over 3 megawatts of power. So prior to the CT, which this pie is showing, really we only made about 4% of the electricity that the campus demanded. Our typical hot summer day electrical demand for campus 50 megawatts. Our cold winter day electrical is somewhere around 30 megawatts. But this electrical generation that we do produce is 100% of our emergency power necessary to feed the buildings. That is for the emergency lighting, egress lighting to get out of a building in a total loss of power. So we can feed that from our emergency cable that is fed from the West Campus Steam Plant electrical generation. As we go through and add this CT with the Herceget East plant, then our electric generation is going to get a little more like 5-to-1 purchase to produced on site. And I've got another pie here that shows, and we'll tell you a little more about this, but there may be some room to put in another CHP. And should we go that direction, we think our electrical demands will look this way. We don't have enough heat load for us to produce all of our on-site power. Our fuel mix, prior to the East Campus upgrade, we were a coal facility. Coal was dramatically less expensive. We had the infrastructure here at West to produce it. West plant came first. So the low pressure comes out of West, and East plant came later, and it was just the peaking plant. So East really, as you can see from here, made about 4 or 5% of the steam per year came from East until we put this project together. And then it started to look a little bit more like, whoops, I went backwards. How about that? As we go through, as we added the East Campus, now your coal gas consumption starts to go over more towards gas. And hey, as our gas prices really came down, again, we developed this project with high gas prices and low coal prices. As those gas prices came down and coal went up, we're burning gas as much as possible. We even have the capability to burn it here at West. As we go through our upgrades at West, which again, I'll tell you a little bit more about what we're doing, but we'll see our coal eventually go away towards 100% gas after 2015 boiler MAC upgrades. A little shot of our efficiency. It's just a a spreadsheet. We keep track of our consumption of fuel and our production of steam and electricity each day. And here you can just see how it kind of fluctuates a little bit here with how we were operating West plant and peaking with East. And then really in June, May-June time frame of 2011, we started full-time with the East Campus Steam Plant running it. And our efficiencies overall for our overall district energy system have leveled out right up there around 70% when it's producing 100% of its power. Thank you. Okay.
So as efficiency is important to Penn State, so is sustainability and greenhouse gas reduction. So if you look at the top line, it is our energy consumption over the past several years. And you can see the green line, which is our greenhouse gases, tracked that energy consumption line for a very long time, and then we committed to, at first, a 17% reduction, and now unofficially we're looking at a 35% reduction. And as you see this wedge shape that occurs toward the end of the graph, and we'll see it here, that's okay, this blue wedge shape, you'll start to see that more and more often, and the biggest reason behind that reduction is that when we put in the CT and we displaced anywhere between 30 to 100,000 pounds of steam with gas fuel versus coal fuel, we automatically saw a greenhouse gas reduction. But we also displaced, millions and millions of kilowatt hours that we bought from the PJM grid. And if you're familiar with the Northeast, we are still over 50% coal on our PJM grid. So not only do we burn a cleaner fuel, but we also make our own cleaner electricity so that we're not contributing in that way to greenhouse gases. So another part of that is not only do we make building improvements through a program called Energy Savings projects, we also have started targeting some energy savings projects at our utilities. So energy efficiency, changing fuels, and this is just a picture of our electric load, which has remained pretty steady. It's the red, and then the coal is shown in the white, and it's starting to go down as our natural gas load is starting to increase. And the oil plays a very minimal role. Again, we use a diesel only as a backup, and that is the light red. Okay, so then the next slide is just an example. It's that wedge shape again, and it shows you where we've concentrated our efforts. And the big black wedge is what we contribute to making that switch to the CHP, the CT and the heat recovery steam generator. The very bottom white wedge is the difference that we'll see because we'll already have been on gas when we go, if we go to a second CT HRSG combination. So,
Shows our CO2 reduction over time. So again, we're heading towards full natural gas operation, and this just gives you a reduction from basically from a coal-fired 200,000 tons a year of CO2 down to a little under 100,000. And our next steps is here at West Campus, we have to comply with the Boiler Act, and to do that, we will change from coal to natural gas, and as part of that, we're looking at a second CT HRSG. So if you remember, our low steam flow in the winter is about 80,000 pounds an hour, and unfired operating just with the CT is about 30,000, so it looks like a second CT fits our load profile. And again, it would go in the West Campus steam plant, replacing, you're looking at 4 coal-fired boilers. Over here you'll see 2 package boilers when the MACT is done. And if the evaluation continues on and we can do it, we put a CT and a HRSG combination there. And just quickly going through there, this is our West Campus CHP, something we've been doing for a long time. And the layout of the West plant, so here's the Boiler Max solution, 2 new package boilers, and keeping the old coal-fired boilers until we could one day find a way to put in a CT with a HRSG. And
so the current program to convert our power plant from coal to natural gas does not include additional funding for a second CT HRSG. We're looking hard at that as being funded through our energy program. And again, Paul just told you what our costs were when we did the first CT. The first CT made sense. Now with the economics change, the second CT is starting to make sense. We have a $60 million budget that is primarily for building and utility energy improvements. This is what I had hoped it looked like. The next slide shows you if we decide to fund the CT HRSG from our energy program, that we do that at the expense of some building improvements. So this is where we are now. Does it make sense to save energy and operate efficiently with a new CT or make improvements in our buildings? The next slide. Again, that was our wedge. That white wedge at the very bottom would go away and actually fold up into the lime green, which is our building improvements, because it would be funded from that project. And then I believe we're finished.
thank you.
Excellent. Thank you, Paul and Laura. Thank you for that very interesting and informative presentation about Penn State University's CHP and energy efficient efforts. With the remaining time, I will pose questions to our panelists that have been submitted during today's webinar. A large number of insightful questions are on our plate, so I'm going to jump right into them. However, before I do so, please note that we intend to answer each submitted question either directly via GoToWebinar's functionality, via email, or during this question and answer session. So, the first question we have on our plate here is for Jay. Jay, why was the NPV negative, or at least it appeared to be, while payback was on the order of 5 years?
Yes, the NPV calculation is compared against the base reference case. So when you calculate a positive IR and payback, it's against which is and they all were negative NPVs, but it's compared against the savings and the differential of the NPVs and cash flow that you see against the base case analysis, which is either the package boiler installation for the new package boilers or against the coal-fired reference continuing coal-fired plant operations.
All right, excellent. Thank you. The next question is for Paul and Lauren. And the question is regarding air permitting. And that is more specifically, have you experienced any unusual challenges in obtaining the necessary air permits for your systems or any of your efforts?
I wouldn't say unusual challenges. I think we have the normal challenges for air permits. The East plant took, it might have been a 12-month process from start to finish by the time we got the permit. But we just went through the normal PA, Pennsylvania Central DEP process.
All right, excellent. Always good to hear that permitting is not an obstacle, as I do personally know that is sometimes perceived to be the case. Now, moving right along, because time is of the essence here, the next one is for Jay. And Jay, given your experience with project development, what is the major barrier to CHP project development, and how best can that challenge be addressed?
Yeah, and I think as each of the owners are industrial sites or institutionals that face this, and I think Paul kind of covered this, is they're really internal as far as capital budgeting process, and just overcoming that is being, as I showed in the total project cost slide, you can see that to consider package boilers versus a CHP plant, that's an order of magnitude difference in cost required, and trying to cover those development projects in a capital budget is a challenge in how you plan and how you approach that, especially if it's like an industrial where power thermal is not your core competency of what you want to focus your investments on. So really that's a large hurdle, is to make that step out to increment that capital expenditures where it's not your core business. And the next one certainly is just understanding the value of the benefit to and the value to the project of considering selling electricity to the local grid and the benefits that provide.
All right, fantastic. We've got another one then for Jay, don't go anywhere, and that is specifically, could you provide some more details on selling energy to the grid? There's a little extra information here, and that is the assumption that the CHP system becomes FERC certified qualified facility? Is there a simple rule of thumb or publicly available data set that indicates what price the utility must or is willing to pay for energy sales?
Oh, and that certainly is part of the DOE and EPA's CHP initiative, is going state by state and developing those scenarios. And what I would say is that if you look at, and it's a different answer for different regions, because if you are in an unregulated region, there are opportunities, depending on the size of your CHP, to maximize the value by participating in those wholesale markets where you might be in New England ISO or ISO New York or PJM as examples, or MISO, and benefiting from trading power versus contracting directly with a local utility for like a power purchase agreement. So, and those are something you have to balance based on a site-specific issue. If you're in a regulated territory where the utility is providing vertically integrated regulated power, or if you're in an unregulated, the options are totally different as far as how you might look at participating in the wholesale market. And when I say participate, transaction go both ways, and that includes access to standby power in addition, and backup power in addition to selling your excess power.
Excellent. Thank you very much. I've been told that I might be not coming through quite so clearly, so I will raise my voice in hopes that everyone can hear me. The next question is for Paul and Lauren. I believe on slide 14, you had a graph or a chart that showed that greenhouse gas emissions from purchased energy had decreased recently. Is this due to reduced purchases of energy or due to changes in greenhouse gas content of purchased electricity? Bottom line, could you elaborate, please?
It's actually due to both, because we're offsetting between 30,000 and 100,000 pounds of steam made by natural gas instead of made with coal. So the greenhouse gases associated with natural gas are lower than those associated with coal. And secondly, we're making about 7 megawatts per hour of electricity with that natural gas, and we're not buying that electricity from the grid. And that electricity from the grid is made with 50% of coal. So we're getting a reduction both from making a cleaner electron and by using natural gas instead of coal.
Fantastic. Thank you very much. We're down to about 4 minutes remaining, so we've got a few more questions I believe we can squeeze in. So next up, another one for Jay. And the question is, what impact have you seen on project viability from the anticipated costs associated with utility interconnection changes and standby charges?
Yeah, and I think that's probably a follow-on from maybe the last question. It is something you have to consider because in certain regions they have been significant in the past. But again, I will say that there are state-by-state initiatives where you're dealing with a regulated utility to I'll say, better facilitate the economics of CHP development, that those standby charges be reconsidered. And as I use the state of Ohio as an example, I know through their PUC of Ohio that they are embarking on, trying to develop new regulations and guidelines that they follow for promoting CHP as it relates to, significant standby charges. If you're in an unregulated environment, certainly those are something to consider, but maybe not as detrimental to the project economics as they would be in a regulated environment.
All right, thank you. We're down to about time for 2 or 3 more questions. The next one is for Paul and Laura. It looks like there's some interest in the financing regarding Penn State's efforts. Specifically, is financing an obstacle for the next phase of the project? And has the university explored third-party financing options? Or is there possibly a reason why you want to keep the project on your own balance sheet?
Traditionally, when we do projects related with energy savings or energy performance contracting, we self-fund that money out of our utility budget because we pay for the project out of the utility budget, the savings hits that utility budget, so in essence you're having a $0 effect to the budget. So complicated third-party agreements have just kept us from going with that kind of option since we can do it in-house. And because the second CT was not in the original design for our MACT project, we are looking at financing it in another way. And right now it looks like the energy projects, which we require an 8-year payback, it looks like that project could meet those requirements financially and economically. Our question is, do we take that $20 million and spend it on the CT, or do we put those $20 million into building improvements? So that's the part that we're trying to find the right answer for right now.
Thank you, Laura. That's been fantastic. Well, with that answer, our time for Q&A has pretty much come to an end. I'd like to notify everyone that all content-specific questions submitted during today's webinar will be consolidated into a Q&A document and distributed to all attendees with information that we mentioned at the beginning of the webinar. So keep an eye out for an email from the EPA partnership with additional information. Jay, Paul, Laura, thank you very much for making your expertise available by participating in today's webinar. And attendees, before you exit the webinar, I have 2 important items. First, please take a few seconds to complete a short survey that will appear on your screen. Your input is very valuable, so please just take 1 minute to complete the survey, which consists primarily of multiple choice. Second, if you would like a recording of today's webinar, that can be made available upon request, while, again, the aforementioned email will be sent out to all of our attendees that will contain a link to the presentation slides. We'll probably include a few more links with general information to the EPA Partnership website with a variety of different resources that our attendees may be interested in. With that being said, today's webinar is finished. On behalf of the EPA CHP Partnership and all of our panelists, thank you all for attending. We hope the webinar was interesting and informative. If you have any additional questions about the material we covered during today's webinar or about CHP resources, please contact the CHP Partnership Helpline